Okay, so I hope we are all ready for a trail. So this is on, basically the underlying theme is tiling, and I thought, and also normal perception about mathematics. Whenever we talk about mathematics, people think of numbers, but there are also shapes, and I thought, of course, shapes and numbers also go together, so that you will see. So we can begin, yeah. Sure. First slide, yeah. So, since tiling usually means, tiling the floor, so you want to tile the floor, a flat floor. So when you want to tile the flat floor, naturally, you would like to make sure of a couple of things. One is that tiles should not overlap, and they should not leave any gaps. Both of them are, of course, undesirable. That's how we would like to tile the flat floor. So normal tiling that you see, for instance, here is all square tiles, because you produce a certain number in the factory and you have to tile the floor, yeah, flat plane. So naturally you have to make sure that when you tile, it should not overlap, nor should it leave any gap, yeah. So how does one start with doing that with one particular kind of shape? Okay, normally people work with regular polygons. Next slide. So if you look at regular polygons, namely, maybe next slide, yeah. So regular polygons. So we have seen that what is the constraint when you want to tile like that. So each tile would mean it has some corners, it has some edges. So when the corners around a particular corner, when you have tiled, which means the space around the corner is also filled up. So when it is filled up, so what should the angle around that corner be? Yeah, actually I would like it to be interactive. So you can also say, yeah, 2 pi, right? 2 pi or 360 degrees, right? So that's all, the simple criterion. And when you look for regular polygons with tile, you have 3 possibilities: equilateral triangles, squares, and regular hexagons. The thing is that, as you know, equilateral triangle, the interior angle is 60 degrees. So if you put 6 of them, you get 360, and square and hexagon. And since from square I moved to hexagon, because regular pentagon, the interior angle is 108. And at each corner you have to put at least 3 of them. But if you put 3, you already sort of little less than 360, it will leave a gap. If you put one more, it will be overshooting 360. You can't do that. Yeah, that's why you don't use only one. You can't actually tile the floor by a regular pentagon. And for the same kind of reason, you cannot tile the floor by regular heptagon and beyond. Yeah, 7-sided regular polygons, because interior angle of a regular 7-sided polygon will be bigger than the interior of the hexagon, which is 120. So if you put 3 of them, it will overshoot 360. So these are the only 3 regular possible. So that's a little too boring. I think people would say, well, only 3 types, what is it? There should be plenty. So you look for combinations of regular polygons. You could use triangles, squares, and so on. So then you get a lot more possibilities. So they are called Archimedean tessellations. I think Kepler classified many of these things, and Kepler is one, he called it Archimedean tessellations. And actually we see some of these tessellation being used. You would see this, and I think you may have seen this in some grills, and you would see the last one is quite popular. That's octagon plus square, 488. All these numbers means, what the meaning is that at each corner point, it tells you, for instance, let's just look at this one. At each corner point, you have a 12 gun. At this point you have a 12 gun, then a triangle, another 12 gun. So that's what it means. So 3, 12 squared. Or you could think of it this way: triangle, 12 gun, 12 gun. Yeah, that's all. 12 squared means 12 times, 2 times. Or here, when you see here, at each point it's 4 square, and then a hexagon, and then a 12 gun. So when you can do this. So I have said that when you want to look for combinations of regular polygons, just as you worked out with only one polygon, just 3 possibilities. The criterion is very simple. Around a corner point, the sum of the angles have to be 2 pi. So you get some 21 possibilities. But not all 21 possibilities can be realized. This is one thing in mathematics. Possible existence doesn't really mean uniqueness in some sense. Yeah. So you could have, and also you should be able to realize that. Yes. So only 8 more, apart from 3, totally 11 can be you could see that you can realize only those of them. You do it only by, that's how they did it. You just have to do it by brute force. You take all these things and try and so on. Whatever fits, you see. If it doesn't fit, then you try to find out a reason. Yeah. Next slide.
So what does it mean? It's not possible to realize.
Yeah. I'll come to the next. It'll come. Yeah. Yeah. Go ahead. Next. So first, let me quickly sketch how I say you can cut down the possibility to 21. Yeah. What does it really mean? Interior angle of a regular k-sided polygon. They have a simple formula. It's pi minus 2 pi by k, and if you just simplify it, it is 1 minus half minus 1 over k times 2 pi. Since 2 pi is one full turn, I'll just kind of think of it as a full turn, and I have n number of polygons, which means different types of polygons, and each polygon, let's say, has one polygon has k1 number of sides, like let's say triangle, k1 could be 3, k2 could be 4, k3 could be 5, and so on. K1 to Kn, n number of polygons you want to put together, and if you want to put together like that, then the sum of the interior angles, right? This is the K1 sided polygon, regular polygon, will have the interior angle to be equal to 1 minus 2, 1 over 2 minus 1 over K1 times 2 pi. So I'll just take care of a full turn. Yeah. So if you add those things, you have to get 2 pi. 1 means basically I have used a full turn, times 2 pi is equal to 2 pi, so I have just cancelled off 2 pi, that's all, yeah. So it has to be equal to 1. This is a very simple arithmetic. Okay, and if I simplify it, you will get this kind of a relation. 1 over k1 plus 1 over k2 up to 1 over k1, 1 over kn is n by 2 minus 1. This is what you will get. Okay, so you can solve, you can see how, first of all, you would actually easily notice that n cannot be really more than 6. The reason is, when you say a polygon, it has to have at least 3 sides, right? K1 is at least 3. Okay, and if I use a regular polygon, which means if I take a triangle, interior angle is 60. Okay, that's the smallest sided polygon I can put. If I put 6 of them, already it's 360. So if you take any other polygon, the interior angle is going to be bigger than 60, so it has to be less than 6 only. Yeah. So n is already 6, you will get that. That's how you kind of, it's simple logic you apply. So it already cut down the possibilities when you, this constraint, it will cut down the possibilities to some 21 only. And question, I mentioned that not all possibilities can be realized. Okay, so you asked the question. So I am giving you one example of a possibility. Namely, if I take 2 pentagons and 1 decagon, so pentagon interior angle will be 108. So if I put 2 of them, it will be 216. It is 144 less than 360. And decagon, 10-sided polygon, interior angle will be 144. So they add up. So if I put 2 pentagons and a decagon at that vertex, you actually can match 360. Okay, so it's possible. Okay, so next slide.